Hello, everyone. Welcome to the webinar on Biphasic Materials Part 2. This is part of the series of webinars that the FEBio team has put together. So I'm speaking here on behalf of my team members, and I will acknowledge them at the end of the presentation. So today I'm going to focus on biphasic materials involved in sliding contact, and I'm going to include frictional and frictionless contact. I'll remind you that the first part of this webinar was given previously. You can find here the links for locating the videos and the recordings. And a biphasic material is, in biomechanics, is the representation of deformable, porous, solid media. And a biphasic material is therefore a porous medium consisting of a porous solid matrix and and an interstitial fluid. And the fluid can permeate through the porous solid matrix. The contact algorithms that will be presented today were detailed in these two publications. Originally, we published in 2010 a paper that described biphasic frictionless contact. More recently, we published a paper in this year that actually describes frictional contact. So the presentation will first look at the unconfined compression creep problem of a cylindrical plug. I'll use symmetry and cut the plug in half, and I'll use this platen, which at first I'm just going to prescribe a normal load to it, and it's going to be frictionless. So we're going to look at the creep response of a biphasic material. Later, I will slide the plate back and forth and add friction. Initially, I'm going to make the solid matrix of the biphasic material be isotropic material, and then I'm going to add fibers to it because most biological tissues are fibrous, and we're going to find out that the addition of fibers will actually enhance the fluid pressure and therefore enhance the part of the load that's supported by the fluid pressure, which we call the fluid load support. I will then talk about continuous fiber distributions because we have an option between discrete fibers and continuous fibers. These are options that are available to us, so it'll be an opportunity to present the features that are present in FEBio. And finally, I'll do more realistic, or I'll illustrate rather, a more realistic contact problem between two biphasic layers instead of a rigid platen and a biphasic material. So my first presentation will be mostly a demonstration. I'm going to create this model. So I'm going to shift now to FEBio Studio. And I'm going to show you how we create a model for biphasic creep. So I'm going to click on the new model option and then select a biphasic analysis. And then I'm going to create a geometry here, which will be a semi-cylindrical wedge. The height will be 1 and the radius will be 1.5 millimeters. And I'm going to create this feature this way. I wanted to actually make it semi-cylindrical, so I need to make this 180 degrees. Now I have this particular geometry, and the next step is to create the mesh. I'm going to create, in this particular case, 16 slices in the circumferential direction, 8 segments, and 8 stacks. And when I create the mesh, you can see that the mesh is going to look like that, nice and uniform. Let me make sure that my units are set to millimeters and Newton seconds. So in the current model, that's what we have. Because I'm going to do biphasic analysis, remember from the first webinar series, we talked about the fact that wherever you have a free boundary, free draining boundary, where the fluid pressure is ambient and therefore set to 0, there's going to be a boundary layer where there's a rapid decrease in the fluid pressure from the inside of the material to the boundary where the fluid pressure is set to 0. So I need to add a biased mesh on this boundary. So to do this, I'm going to convert this mesh to an editable mesh. Then I'm going to select the lateral boundary, and I'm going to do this by selecting all the faces in one step. So you can see all these lateral faces have been selected. I'm going to click on the boundary layer tool. I'm going to use a bias of 2, and I'm going to use 5 segments. That means I'm going to divide this layer of elements here into 5, and each element will become twice as thick as the previous one as I move away from the boundary. That's what the bias represents. When I say apply, you can see that's exactly what happened. I created a boundary layer mesh. Now, I'm also going to do a contact analysis. And when I do contact analysis, especially if I add friction, I need to resolve the fluid pressure at the contact interface very nicely as well. So in this particular case, I'm also going to select the top face, and I'm also going to create a boundary layer going down in order to get very fine mesh to resolve the fluid pressure, because we're going to find out later that when we add friction, the friction will be proportional to the magnitude of the fluid pressure relative to the contact pressure. So this completes the creation of the mesh. Now what I would like to do is I would like to, so we'll just name this our tissue. I need to create the geometry for the loading platen. So for the loading platen, I'm going to go back to the Create tab, and I'm going to select the patch. For this patch, I need to decide where it's going to be located. I'm going to first center it at the origin. And I'm going to make it wide enough that later I can slide back and forth along the X direction. So remember, the diameter of this plug is 3 millimeters. So I'm going to make the platen be 8 millimeters wide. And in the height, remember, I have 1.5 millimeter radius, so 3 millimeter diameter, and the tissue is not going to expand a whole lot. So I'll make the height be 4. So then I can create this platen, and now it's located there. I need to mesh it, but because I'm going to make the platen rigid, then I only need one face because it's planar, and the contact analysis will run just fine with only one face because it's going to be planar and rigid. So now I'm going to rename this part. I'm going to call it the platen. However, the platen is located in the wrong location. I want it to be at the top of the tissue. So when I want to move it up, I need to use to translate it up. So I'm going to use the edit and transform menu option, and then later I can use this shortcut if I want to make changes. So I would like to move it up by a particular distance, but actually it's not enough to move it up. So before I actually enter a value to move it up, I actually want to show you something. If I hide the tissue, and if I go to the view menu and I say toggle the normals, which is going to be here, show normals, then you can see that the normal to this face is facing up. So if I actually want to do contact with the top face, I got to flip this platen so that the normal of the top face is pointing down against the normal, the outward normal of the tissue face. So that means that when I do my transformation, first I should rotate by 180 degrees, let's say about the x-axis. If I do this, then what you will notice is that the normal actually did shift down. So now the normal is pointing in the correct direction. I can toggle it off by pressing on the keyboard letter N, which is the shortcut. I'm going to show the tissue again. And now I want to move the platen up by the height of the tissue. But if I move it to exactly 1 millimeter, then that means that initially when I apply load on the platen, the contact will not be engaged because there will be zero overlap between the platen and the tissue. If the contact is not engaged, then the contact force is 0 initially. And so that means that if you apply a force on the platen, which is downward, there's no contact force to counter it, and you cannot satisfy sum of forces equal to 0, then the analysis will fail. So in order to engage the contact from the very first iteration of the very first time step, you should let the platen overlap the tissue by a little bit. How much is a little bit, honestly, is a trial and error choice. Here in my case, the height of the tissue is 1 millimeter of the plug. So I'm going to translate the platen in the Z direction up to almost 1 millimeter, but it'll be 0.999. So it'll be 1 micron short of 1 millimeter. So now I have moved the platen to the correct location. Let me save this problem. I'll put it on my desktop, and I'll call it unconfined compression, and it's going to be creep. And I'm going to say no fibers, because in this particular model, I'm not going to put fibers. And this, by the way, is going to be the name of the file that you can find in the repository. All the models that I'm going to create today have already been created for you, and they can be found in the repository. So you click on this tab down here, you click on connect. And in your case, you're going to see all of these. You should expand the webinar folder. But this particular webinar was uploaded by me. So therefore it appears in my user project. So in my case, it'll show up here. So if I expand it, you will see all the files that are in here. The unconfined compression creep with no fibers is located here. You can double click on it to get the model that I just got. But for now, I'm just going to continue working with the model that I'm creating here. So now what I have is the geometry. I need the material properties. So the next thing I'm going to do is I'm going to add the material, and I'll start with the biphasic material. So this will be the biphasic tissue. That's just the name that I'm giving it. So I'm going to select here bi, tri, multiphasic. Under the material, I'm going to select the biphasic material. I'm going to make the solid matrix. I have only a ground matrix, which is Nahookian, which is, isotropic. So the Nahookian material is down here. I'm going to pick a simple model for the hydraulic permeability. I'll make it constant and isotropic. And there's no solvent supply in this particular material. And I can click on the plug and click on the plus sign here. And now I've assigned this material, although I haven't yet provided the material properties. The details about the meaning of these material properties can be found in the previous webinar. So I'm not going to go over these. All I'm going to do is I'm going to pick here a ground matrix modulus of 1 megapascal, Poisson ratio of 0, and for the hydraulic permeability, a good value for articular cartilage in this system of units would be 0.001 millimeter to the fourth per Newton second. So now I have created the material and assigned the material properties, and I've assigned the material to the plug. I still need to create a material for the platen, and this material is going to be a rigid material. So I'll call it rigid platen, but again, the name means nothing. It doesn't mean that it's going to be rigid unless you select the category called other, and under other, you select rigid platen. When you do this, then you can click on the platen, click the plus sign, and now this has been assigned. These properties here are not going to matter for a rigid platen in the application. So in this particular case, now I have the geometry and I have the material properties. So I'm ready to apply the boundary conditions. The boundary conditions I'm going to apply are going to be as follows. First, I can turn off the mesh for a second. I'm going to fix the bottom of the plug because later when I do friction, the platen will move back and forth. And so I want to prevent the plug from sliding. So I'm going to fix all the degrees of freedom. I'm going to go to the physics menu. I'm going to add a boundary condition. Later, I'll just use this keyboard shortcut. And for this boundary condition, I'll take fixed displacements and I'll fix the 3 components of the displacement along X, Y, and Z. And then I'm going to remind myself that this is a symmetry plane. Therefore, I really need to prevent any displacement along the Y direction. So I'm going to once again create a displacement boundary condition here and constrain the Y direction. And then finally, I want a free draining lateral boundary. So I'm going to pick this lateral boundary and I'm going to say that I want 0 fluid pressure on here. And don't forget to check the box here. So that applies the boundary conditions on the tissue. But I still need to apply boundary conditions on the platen. There are 2 kinds. One where I fix the degrees of freedom that I don't want to move, and then one where I apply the load. So I'm going to go to physics and I'm going to say add rigid constraint. And I'm going to name this constraint fixed degrees of freedom for the rigid platen. So that's the only rigid material available in the model. Therefore, it's already selected for us. I'm going to pick fixed rigid displacements rotations. And I'm going to fix the X displacement, the Y displacement, but not the Z displacement. Since I want to apply a load in the Z direction, I want it to creep in that direction. And the other 3 rotations, I'm going to fix them as well. So this will fix the 5 degrees of freedom, but then I want to prescribe a load. So I'm going to say the platen load is the name that I want to give it. And this time I'm going to say prescribe a rigid force. So this rigid force is going to be on the rigid platen. Again, that's the only rigid material available in the model, so it's already selected. I want it to be in the Z direction, and I want it to be pointing down. I want to apply compressive load in the opposite direction than the positive Z direction. Now, the value of the load is in newtons. By trial and error, I've decided that 1 Newton is actually a good choice for this particular problem. Okay, so then we have applied the load on this material. Now, the load always comes, any prescribed displacement or load comes with a load curve. So if I go to my rigid constraint under the platen load, what you will see is the load rises from time 0, it'll be 0. And then at time 1, which you see here is time 1, it'll rise to this value, which is 1 times whichever value I entered. In my case was -1 Newton. So at time 1 second, I'll have -1 Newton. And I'm satisfied that this is good. Normally you would say, well, a creep problem should be a step load. The answer is yes, but it turns out that 1 Newton load is going to cause finite deformation. So really we should ramp it up relatively quickly. So 1 second over the time duration of our analysis. So I have now all the boundary conditions. I need to set up my analysis. I go to the physics menu and I say add analysis step, and I select the biphasic analysis. I want to, the first thing I need to do is decide how many time steps, what's the time increment. So I want to run this analysis to up to 10,000 seconds. That's because, I pick the hydraulic permeability and the dimensions of the material and a hydraulic modulus such that the time constant is on the order of 1,000 seconds. So I'll run it to 10,000 seconds, but I want to apply the load in 1 second, and I would like to have the load increase by 10 time steps. So I want the step size to be 0.1. Therefore, I should pick 100,000 time steps times 0.1 second will give me a total of 10,000 seconds. However, I'm not going to run 100,000 time increments. That would be crazy. So for the maximum step size, instead of specifying a value here, I'm actually going to create a must point curve. So that's what I'm specifying. In a second, I'll actually use the load curve to modify the must point curve. But for now, let's continue with what we're doing here. I'm going to run an analysis which involves contact and biphasic material. So I should pick a non-symmetric stiffness matrix. I'm going to use full Newton iterations, not BFGS, not Broyden, even though for non-symmetric it should be Broyden. But in order to do a full Newton analysis, the maximum updates will be 0. I use full Newtons because contact analyses converge better with full Newton. And I'll pick, to be safe, 25 maximum reformations, but I'm fairly certain that I'm going to be able to converge in less than that. So for optimal iterations, I don't want to take shorter time increments than what I specify in the must point load curve. So I'll pick the optimal iterations to be the same as the maximum number of reformations. And then I'm going to go and modify the load curve for the must point. So I'm going to expand here under steps, and I'm going to connect the must point load curve. Normally it's a step, but I'm going to make it linear. I want it to go from, I want it at time 0 to be 0.1. I want the smallest time increment to be 0.1 second. At time 1, I also want it to be 0.1 seconds. So from time 0 to time 1, I wanted to make sure that it's a 1 second, 0.1 second increment. But then all the way to time 10,000 seconds, I want the time increments to rise linearly to up to 1,000 seconds. So now what you see here is that as time progresses, as the analysis progresses, because it's a creep problem, I allow the time increments to increase accordingly. So that means we're going to run much fewer than 100,000 time steps, which thankfully is the case. So now, in principle, I'm ready to solve, except that the one thing that I haven't done yet is to create a contact interface. So I actually forgot to do that earlier. I'm going to now add the contact interface. I'm going to add my biphasic contact interface. So I'm going to scroll down here. I'm going to select biphasic contact. For biphasic contact, I need to pick a primary surface, and usually you pick the deformable. If you have deformable material and a rigid material, you always pick the primary surface to be the deformable material and the rigid to be the secondary surface, the rigid material to be the secondary surface. That's because we calculate the contact parameters from the primary surface to the secondary surface. And there are many faces on the primary surface because we created a fine mesh. There's only one face on the secondary surface. So that's one thing that you need to know about how we set this up. Then I'm going to hide the selection of these faces. I'm going to keep the defaults for everything that we see here for the biphasic interface, except, so I have a penalty factor of 1, 2 pass no. That means I'm only going to throw a ray from the deformable surface, the primary surface, to the secondary surface, which makes sense because I have a rigid platen. But I want the auto penalty to say yes. So the contact stiffness that comes from the contact algorithm, this is all explained in the webinar on contact mechanics that Steve Moss presented, webinars 2 and 3. So please review those webinars as well. So now I have created the contact interface. And because I'm going to look at the results in a moment, I'd like to include in the plot variables everything that's related to contact. So I'm going to filter the plot variables with contact, and I can select contact area, contact force. Contact gap is how much artificial overlap I allow between the platen and the biphasic material. I'll get the contact pressure, and for now, that's going to be good enough. Then I want additional variables related to the fluid. So I'm going to calculate the fluid force, how much, the integral of the fluid pressure at the contact interface, the fluid load support, which I'll talk about in greater detail later, and the fluid pressure within the elements, whereas the effective fluid pressure is the nodal fluid pressure. And I'm going to get something called the local fluid load support to display what it looks like, because it turns out it's a critical value for the biphasic friction algorithm. So what we have here now is we've established all the parameters. I'm ready to run the analysis. I'm going to say run. This particular analysis should run in about 2 minutes. So while it's running, I'm going to go back to my slides and explain to you what we did. So we picked an Nahookian isotropic solid matrix, constant isotropic permeability. We prescribed not a step compressive load, but we ramped it up in 1 second. And we let the platen overlap the biphasic contact surface slightly to engage the contact at the initial time. And the amount of overlap was 0.001 millimeter, which is 1 micron. We picked the primary surface to be the tissue, the secondary surface to be the platen. We turned on auto penalty, and we kept all the other default values. Then for the biphasic analysis, we used linearly increasing time increments. So this is a summary of what we just did. In a moment, I'm going to show you the results. What we're looking at here is the platen displacement over time. So the horizontal axis is time. It goes to 10,000 seconds. And what you see is the creep response. And it's negative because the contact is downward. So the displacement is in the negative z direction. What you see is the displacement is going to be roughly negative 0.25 millimeters. So it's actually 1/4 of the full thickness of the initial thickness of the plug. That's why it's a finite deformation analysis. And we reach steady state in about 3,000, maybe 4,000 seconds, let's say. That's the time constant that we reached. If I didn't increase the load linearly at first during the first second, then you wouldn't see so many points here. You would see just a jump. If I had applied a step load, I would have had a jump from this point to this point. So that's how you have to interpret these intermediate points here, because initially when you first apply the load, the tissue is going to expand laterally. And when it expands laterally, it's kind of a sudden jump if you applied the load suddenly, but we applied the load in 1 second. And then what we are going to look at in a moment is the solution that we found. So when we look at the solution, one of the more interesting things that we look at in a biphasic analysis is the fluid pressure. And the fluid pressure itself is part of the mixture stress. So the mixture stress in the material is the sum of the fluid pressure plus the stress due to the deformation of the solid matrix, in our case, the Nahookian solid matrix for now. So this mixture stress produces a mixture attraction when you project it along the unit outward normal to the contact interface. This mixture attraction has a normal component, which is the contact pressure, and a shear component, which is the friction. In our case, we had frictionless contact interface, so this has only a normal component. The normal component of the traction can be decomposed into the contribution from the fluid pressure and the contribution from the deformation of the solid matrix. So this is the stress due to the strain in the solid matrix. We define the fluid load support as the ratio of the fluid pressure to the contact pressure. The negative sign is just because by convention, the pressure is positive in compression, whereas the traction is negative in compression. And if we plot the local fluid load support, we call this the local fluid support because we can define it at every point on the contact interface, then what you can see is it's higher at the center and it decreases towards 0 at the periphery. And that's not surprising because we requested that the fluid pressure be 0 at the periphery. So let's see if the analysis finished running. The answer is yes. And it took about 1 minute and 29 seconds on my computer here. If I display the results, we can see some of these results that we just discussed. So first, let's play this animation. You can see the load was applied in 1 second. And then over time, we're going to see that the material is going to creep longer and longer. I can turn on the effective fluid pressure. You can see the fluid pressure is high at the center, but 0 at the periphery. If I go back to the very first time step, you see initially you actually get the fluid pressure for this particular choice of constitutive model is higher down here because there's a lot of lateral bulging of the tissue down. But if I display the local fluid load support, which is the plot variable here, it only shows up on the contact interface. And you can see initially the local fluid load support is very high everywhere, or very high, on the order of 45%. And then over time, well, it increases locally at the center, but over time, you're going to see that it's going to start decreasing. And eventually, the fluid load support should go to zero when the fluid pressure goes to zero. And indeed, as time increases, you can see that this fluid load support goes to zero. The color scale is automatically adjusted at each time step. So now let's go back to the slides and take a quick look. And now what I want to do is I want to talk about how we can do a more realistic model for biological tissue. Instead of assuming that the solid matrix of the biphasic tissue is just isotropic and behaves the same in tension and compression, we're going to add discrete fibers, for example, to represent collagenous tissues, such as the solid matrix of articular cartilage. So when we add discrete fibers to our model, that means we can add fibers in specific directions. We can use a solid mixture to mix the ground matrix, which will keep it to be now Hookean. Then we'll include fibers, and these fibers can only sustain tension. So therefore, there's no sense in putting fibers in the direction of the loading in the Z direction, because those will buckle. In the example that I'm going to give, therefore, we're going to add two fiber families, one in the radial direction, one in the circumferential direction, which means that I'm going to have to explain how we define local material axes. So because of the cylindrical geometry, I can actually generate local coordinate systems for each element using this feature that I'm going to show you. I'm going to demonstrate it in a second. And then what we're going to find is that the local material axes will be, the red will be the local X direction, the green is the local Y direction, the blue is the local Z direction. And then I'm going to add fibers that are aligned with the red direction. So now I'm going to use the angles option. I have a spherical coordinate system for specifying fibers. So I'm going to put one fiber family in the radial direction, which is the red direction, and that will correspond to this phi angle, the spherical angle, from the Z axis down to the X axis is going to be 90 degrees, and the angle relative to the X direction is going to be 0 degrees. That's going to be the radial fiber. And for the circumferential fiber, which is the green one, I'm going to use phi is 90 degrees and theta is 90 degrees. So let's do that. And I'm going to call this model UC creep discrete fibers. So I'm going to save the existing file that we created under a new name. So I'm going to close the plot file, and I'm going to modify this file. I'm going to say save as, and I'm going to say discrete fibers. So unconfined compression creep discrete fibers. And I'm going to save this file here. So I'm going to now show you how we can add the fibers to our material. And first I need to show you how we're going to create the material axis. So to create the material axes, let me hide the platen because it's in the way. So I hide the platen, and then I select the tissue, and I'm going to use this feature here, which says set fibers. So in order to set the fibers, first let's view the default orientation of the material fiber. So I'm going to toggle the material axes, and what you can see here is by default the material axes, I'm going to switch to the wireframe mode by pressing the keyboard letter W. The wireframe mode here is showing me that by default the x-axis of each element is along the global x-axis. The y-axis of each element is along the global y, and same with the global z. So now I'm going to modify this default by clicking set axes. And there are many options here. I'm not going to describe them all. I'm just going to pick the one that's cylindrical because we happen to have a cylindrical geometry. And for the cylindrical material axis generator, the vector A represents the axis of the cylinder, which in our case should be pointing in the Z direction. So I'll pick 0, 0, 1. And the D vector represents the radial direction for the X direction. In our case, it'll be 1, 0, 0. If I say apply, suddenly you see all these axes change their orientation, just like we expected them to. So now we have the red is radial, the green is circumferential, the blue is axial. So now we have the material axes in the direction that we want. So I can change the material representation. So let me toggle the material axes off, and let me exit the wireframe mode and maybe get rid of the mesh. I'm going to focus now on the biphasic material. So I'm going to modify this material as follows. For the solid matrix, instead of having Neo-Hookean, I'm going to change this and I'm going to make it a solid mixture. Remember that I said that I want a mixture of multiple constituents. So I'm going to change it to solid mixture, and there's no solid components yet. So I'm going to add the first one. Once again, is going to be the Neo-Hookean ground matrix, and I already know that I want the Young's modulus of it. So we'll keep it that. Then I'm going to add a fiber. We have many fiber materials. I'm going to pick this fiber exponential power law, but I'm going to only use the power law relation. So that means the exponential coefficient is going to be 0. For the power law, I'm going to pick a strain energy density, which is quadratic. So I'll put the parameter beta will be 2. And C is the fiber modulus. In the slides, I'm going to pick 2 different values, 5 megapascal and 50 megapascal. But in this case, I'll just pick 50. And again, I have to go back to my preferences, make sure that my units are set, because it was only set for the previous model. So now when I turn on the units, you can see this is going to be 50 megapascal. Then I need to specify the orientation of this fiber. And remember, we're going to pick those spherical angles, theta and phi. And the default values are the values for the radial fiber. So 0 and 90. So I'm going to keep those. I'm going to add one more fiber. This one will be the circumferential fiber. I'm going to pick exactly the same fiber model, the same material properties. So an exponent of 2, a fiber modulus of 50, but this time the fiber angles are going to be theta is 90 and phi is 90, just like the slides. So everything else is the same. So this is very nice because it shows that, in fact, there's very little that we need to change to go from a non-fibrous solid matrix to a fibrous solid matrix. So in principle, I'm ready to run this analysis, and I'm going to run it again. But this one will take maybe a little bit longer, not a whole lot longer, because I added 2 fiber families. So I want you to know that if you actually want to display the fibers, there's a plot variable that lets you, specify the fiber and give it a name and the radial direction. This can be added manually because we're actually looking at the fibers within a solid matrix. And so FEBio Studio doesn't know that you're going to use a solid mixture to include fibers. So if you do, then it gives you the option to manually add this. I'm going to skip this particular detail here because it's not terribly important. You can see the fiber orientations with the material axes. Let me discuss the results that we're going to see. So the biphasic time constant to reach equilibrium was discussed in the previous biphasic webinar, but I'll just say it's proportional to the tensile or inversely proportional to the tensile modulus of the fiber. So when you include a tensile fiber, then the time constant will be shorter. So it turns out that when you add discrete fibers, you're going to reach steady state faster. This is the creep displacement, but on a logarithmic time scale. And this is the initial displacement at the end of 1 second for the discrete fiber. This is for the no fibers. Okay, so what we see is that initially, when you don't have fibers, then the tissue expands laterally a lot, which means it'll compress axially by a significant amount. That's this jump from 0 to this negative 0.12 millimeter here. But if you add fibers in the radial direction and the circumferential direction, when you apply a load initially, the tissue doesn't really want to expand a whole lot. It expands much less. But then it's going to creep a little bit faster. So if you kind of pay attention, it's kind of on a logarithmic scale, but it reaches steady state in about 2,000 seconds instead of roughly 3,000 to 4,000 seconds earlier. So the tensile stiffness of the matrix holds the tissue in. You get less bulging down here, which was problematic for the final element analysis, but now there's less bulging, which is nice. The interstitial fluid pressure will increase. Physically, the reason is the following. You're applying the same amount of compressive load. Initially, the compressive load was being supported by the fluid pressure and the solid matrix, which had very little, compressive stiffness. It has only 1 megapascal stiffness. So you're compressing it and the tissue is expanding laterally. But now if you add fibers in the radial and circumferential direction and you try to compress the tissue, it doesn't want to expand laterally as much as shown here. If it doesn't want to expand, how is it going to support the same amount of load if the solid matrix deformation is even less? The answer is the only way it can do it is by increasing the fluid pressure. And indeed, you see that the fluid load support increases from roughly, on the 40% level to upward close to 90%. And let's take a quick look and see. This analysis did converge. It took the same amount of time as before, which was nice. So about 1.5 minutes. So now I can show you here the local fluid load support. And if I play it, you can see the local fluid load support is actually much more uniform initially and much closer to 100%. And then over time, it decreases. So you can see how much more fluid load support we got here. And if you want the average of the fluid load support, you can actually select one of these faces here. We don't need to select all the faces. So I'll select only one of the faces. I'll say post new graph. And of course, I can look at the local fluid load support for this particular face. And for this particular face, I can zoom in at this particular location. You can see it goes really high. It reaches 99%. But really, I want the average of the local fluid load support over the entire contact interface. And that's going to be the plot variable called fluid load support. This average is also going to be close to 100%, but not as high as the local one, because at the edges, the local fluid load support is actually going to go down to 0. So here you can see that we reach a maximum of roughly 98%. So this fluid load support is going to be important later on when we talk about friction. So that's the result. And you can see also if I can hide the platen and I can look at the tissue from the side like that. And you can see that there's very little lateral expansion during the application of the load, contrary to the case with no fibers. So you can see it creeping downward, but it doesn't expand much, laterally. Okay, so that explains to you, the results presented. Now, discrete fibers is one way of representing a biological tissue, but many biological tissues have a lot of fibers, collagen fibers going in multiple directions. So you can go ahead and add in your solid mixture a dozen fibers if you want, or you could say, I'd like to model a continuous fiber distribution. So that option is also available in FEBio. Whether one is superior to the other, there are pros and cons to both approaches. But if we want to use a continuous fiber distribution, once again, you use the solid mixture, you include your ground matrix, which in our case is now Hookean. And this time, instead of discrete fibers, you actually include a material called continuous fiber distribution. And there are many available options. The default or the simplest one is what we call the 3D spherical or isotropic. So what you need to imagine is that each material point in the tissue is at the center of the sphere, and you can throw a ray in any direction, and that gives you where you intersect the sphere is the fraction of fibers that are oriented in that direction. Because the sphere has the spherical symmetry, that means that there's equal number of fibers going in all directions. That's why we call this a spherical fiber distribution. But if you want to have preferential fiber orientation along a particular direction, you can also create an ellipsoidal distribution. There will be more fibers in this direction than in this direction. But what if you want only fibers in predominantly this direction, none in that direction? That option is not really available to us with an ellipsoidal distribution. So we can switch to the 3D von Mises, which allows you to pinch the waist. You can see this peanut shape here. You can pinch it as much as you want. You can pinch it down to the point where there's 0 fibers going in this perpendicular direction. This, let's say, is the predominant fiber direction. So this is a 3-dimensional fiber distribution. But what if your tissue has a planar distribution? Let's say it's like the arterial wall, and there are very few fibers going out, in the radial direction. They're only in the circumferential or the axial direction of the artery or of the arterial wall, in which case you can do a 2D distribution. You can have isotropic in the 2D plane, which would be a circle, or you can have it, transversely isotropic or orthotropic. So in this case, it would be actually elliptical. Or you can have this von Mises distribution where you can pinch the waist. So there are only fibers. This is a polar plot. There are only fibers going in this direction, none going in this direction. And if you go at this angle, there's much fewer fibers. It's wherever your line intersects this curve tells you what's the fraction of fibers in that direction. So these are options available to us. What's important to understand is I gave you here the symmetry, the material symmetry of the fibers if all the fibers are in tension. But remember that the fibers can buckle depending on whether this particular fiber is in tension and compression. So some of the fibers could buckle, so the actual material symmetry of your material changes with the state of strain. So you actually could drop to lower symmetry than the symmetries indicated here. So you could have a fully triclinic or monoclinic symmetry, for example. Also, continuous fiber distributions mean that you have to evaluate many fiber directions, usually several hundred to get an accurate result. So that the computational time for continuous fiber distribution increases. So I'm going to now show you how we do a continuous fiber distribution, but I'm going to pick a simple material model. So I'm going to, once again, modify the model that I had created earlier, which had no fibers. And I'm going to save it now with a new name. I'm going to say save as. Instead of saying no fibers, I'm going to say undefined compression creep, continuous fiber distribution, which I will abbreviate as CFD. So now the material orientation doesn't matter because I'm going to pick a spherical symmetry. So I'm going to go to the material tab and I'm going to modify this material. Instead of having a solid matrix, which is only Neo-Hookean, I'm going to make it a solid mixture once again. And for the solid mixture, once again, I'm going to have a ground matrix, which is Neo-Hookean, which has a modulus of 1 megapascal. And I'm going to now select a continuous fiber distribution as the second solid in my matrix, in my solid mixture. And the axis here, I don't need to specify because a spherical fiber distribution is symmetric, spherically symmetric. But for the fiber model, I'm going to pick fiber x pow, and I'm going to pick the exact same material properties that we did earlier. However, what you need to understand is even though I'm picking 50 megapascal for the fiber stiffness, previously I had two discrete fiber bundles, each at 50 megapascal. Now I'm taking a net number of fibers and I'm distributing them uniformly in a spherical distribution. So along each direction, the effective stiffness will be lower than the discrete fiber model. The distribution that I have here is going to be spherical. That's what I said earlier. And then there's an integration scheme that you have to pick. You should not pick the one that says 2D, even though it seems like it's an option here. You should pick one of these two options. This one is the older one. It requires more integration points. This one is the Gauss-Cronrod trapezoidal integration scheme. It requires fewer integration points, in this case, 11 times 31. So several hundred, obviously, but not thousands as the FEI scheme would require. And everything else, I'm going to keep it the same. I'm going to save this material. We're ready to run. But because it's a continuous fiber distribution, this one will run in much longer than a minute and a half. So I'm going to let it run, but we're not necessarily going to come back and see the results. I'm just going to explain what we're going to find. We're going to find that the creep displacement for the continuous fiber distribution, well, I did two cases here, one with fibers of 5 megapascal, one with fibers of 50 megapascal. If I do 50 megapascal, I can actually match the stiffness of the discrete fibers reasonably closely. But if I do 5 megapascal, I have less creep displacement initially, or rather more creep displacement initially. So here's then the response with the continuous fiber distribution is the yellow curve versus the orange curve. And the fluid load support, it rose with the continuous fiber distribution and the fiber modulus of 5 megapascal relative to the no fiber model, but less than the discrete fiber model. But for the continuous fiber distribution here, I'm reaching an interstitial fluid load support of 100%. So that's why it's sometimes useful to understand the importance of incorporating continuous fiber distributions. Once again, we get very similar behaviors as the two discrete fiber families that we had. Fine. So why am I emphasizing the interstitial fluid load support? Because it actually matters a lot in relation to cartilage friction. Now, I had showed some of these results in the previous webinar. This is just looking at a piece of cartilage that was loaded in this confining chamber under a creep configuration. And we measure the total load with this load cell, but we can also measure the fluid pressure at the articular surface. We flip the articular surface down against this MEMS pressure transducer, and we can measure the fluid pressure at the articular surface at the same time that we're measuring the applied load. when we actually report the results, and this is the applied stress for the creep problems, about 0.06 megapascal, and the fluid pressure pretty much reaches the applied stress and decays over time back to zero. And so this fluid pressure here slightly exceeds, the applied stress because, we are measuring the fluid pressure at the center. And so the fluid pressure is not exactly uniform across the whole surface of the sample. If it were uniform, then it should be exactly equal to the applied stress. If you now take the ratio of the fluid pressure to the applied stress, you get what we call the fluid load support. This is the load supported by the fluid pressure divided by the total compressive load. And essentially, it's equal to 100% initially. But as the fluid pressure goes down, because the fluid is slowly leaving the tissue through the porous filter that we use to load the tissue through its back. So then over time, the fluid pressure will go down to zero. So this is what we call the fluid load support experimentally. Now let's show how we measure the fluid load support while we're also doing friction measurements on cartilage. So we have this cartilage plug placed on top of this, porous, grid, which is on top of this pressure transducer hole. So then the fluid pressure will be more uniform. The fluid pressure that we measure with the pressure transducer will be the average fluid pressure, more or less, over the whole bottom of the sample. Then we're going to slide this glass slide on top of the sample. We have a motor that's going to move, the bottom relative to the top. So here's the glass slide, here's the tissue, and we're measuring the fluid pressure. And we're going to measure the frictional force with this multi-axial load cell. So we're going to get the force in the horizontal direction will be the friction force. The force in the vertical direction would be the contact force. Then we can take the ratio of the friction force to the contact force, and that'll be called the friction coefficient. And here's the friction coefficient. We call it the effective friction coefficient, and it rises over time because we're doing a creep problem. And after 20,000 seconds, it reaches more or less a steady state value. We call this the equilibrium friction coefficient. So initially we have a very low friction, and over time it increases to a non-negligible value on the order of 0.25 to 0.3. At the same time, however, we're measuring the fluid load support. The fluid load support is almost 100% initially, and eventually it goes down. So it's not a coincidence. It would be too much of a coincidence to say when the fluid load support is high, the friction is low. When the fluid load support is low, the friction is high. You're bound to think these are related, and that's what we thought when we did this study back in 2004. So if you plot on the horizontal axis the fluid load support, on the vertical axis the friction, so we eliminate time. This is what we call a parametric plot. We eliminated time as the parameter. And what we have is when the fluid load support is high, the friction is low. When the fluid load support is low, the friction is high. So the data follows pretty much a straight line. So it makes sense to propose a constitutive model for the friction, which says that it's going to be a linear function of the fluid load support. This linear function is not just 1 minus the fluid load support. It turns out that when you actually do a linear regression, you need to have a non-unity coefficient here. And that non-unity coefficient, we interpret it to be the fraction of the contact, which is fluid coming in contact with the platen. So phi is the fraction of solid on solid contact. You have a porous cartilage surface coming in contact with a non-porous glass. If the porosity of the cartilage is 90% at the articular surface, then that means only 10% of the apparent contact area of the cartilage represents collagen coming in contact with the glass. So indeed, when we actually fit this linear regression to the experimental data, we find that phi is roughly 11%, and the equilibrium friction coefficient seems to be about 0.3 in this case. When we measure directly the porosity of the tissue in the articular surface, we find that it's 90%. So that means the solid fraction is 0.1, very close to what the regression showed. And the equilibrium friction coefficient, we just take it to be the final value, is pretty much the same as the value B. So this experimentally validated friction model is what we implemented in FEBio. But I want to point out to you that we're using here the fluid load support, which is the average of the fluid pressure over the entire contact area divided by the contact force. So this fluid load support in this old biphasic friction theory uses the integral of the fluid pressure over the contact interface and divides it by the contact force. But in the biphasic friction algorithm that we have in FEBio, we don't want to integrate over the whole contact interface. We know the fluid pressure at every point on the contact interface. We know the mixture traction, the normal component of the mixture traction. So we actually use a local fluid load support, which is different from the fluid load support that we used in our previous experimental studies. And the average of this local fluid load support is generally different from the ratio of these two forces. So you can see the mathematically, this ratio here, which is the average of the local fluid load support, is not the same as WP over W. So in FEBio Studio, we're going to use this value, but I want to make a statement about what this value would give us in some cases. So in the biphasic frictional contact algorithm, we modified the algorithm to use the local fluid load support. And remember, we have a negative sign because of the convention that the fluid pressure is positive in compression, but the contact fraction is positive in tension. So now we have a friction coefficient, and the user specifies what fraction of the contact interface is solid on solid contact. There's a theoretical maximum or minimum value for the friction coefficient. Based on the second law of thermodynamics, you cannot get negative friction coefficient, so we want the friction coefficient to be positive. So if you impose this constraint on this constive model, it actually says that the local fluid load support must be less than this ratio. Now, if phi is 0, then this ratio is 100%, but if phi is 0.1, it's more like 111%. So the maximum allowable fluid load support could be greater than 100%. And it depends really on your choice of the solid to solid contact area fraction. So if numerically during the solution of the biphasic contact algorithm, if there's numerical errors, round-off errors that cause this number to be greater than this theoretical maximum, then FEBio will enforce this maximum locally. Okay, and it'll override any higher value. So that means you will never get a local fluid load support that exceeds this theoretical upper bound. Now, however, when you have a non-realistic material model, let's say you have a continuous fiber distribution and you make it continuous at every point all the way to the articular surface. Now, this is a constive model that you created, which puts imaginary fibers in the model. These fibers are pointing in every direction, but at the articular surface, really, there should be no fibers pointing out of the articular surface or the contact interface. So therefore, if you actually create a non-physical model of your biphasic material, you can actually exceed this theoretical maximum by a lot. So therefore, one should be careful not to use non-physical models like this. And I'm going to illustrate this point in a second. Basically, the reason why this happens is because if you have fibers that stick out, some of them can be in tension, depends on the state of strain in the tissue. And there's a theoretical paper that we wrote a while back that explains that there's a cone of strain. This is the normal strain along the fiber, and you're either inside the cone or outside the cone, depending on whether 2 of your 3 eigenvalues of the strain are positive or 2 are negative and the other one is positive. Anyway, I'm showing here that these fibers would be in red if they're in tension. So if you project along the vertical direction, that means you're actually having a tensile contribution to the normal traction, which decreases the value of Tn relative to the case where you cannot have tensile fibers going out. And that means that you can exceed the theoretical maximum because of this non-physical assumption. Okay, so how do we avoid this non-physical model? What we do is, here's just the illustration. So if you actually went and used the integrated fluid pressure, let's see if this model actually converged. It did. So in addition to the fluid load support variables that we had, I'm going to illustrate this briefly. I can hide the rigid plot, and I'm going to select one of these faces here. Remember, I told you that there's a plot variable called the local fluid load support. It cannot exceed 100%. So if I zoom in on here, or it cannot exceed the theoretical maximum, you can see that it wanted to exceed it, but FEBio forced it to remain, equal to the theoretical maximum. In this case, by default, the parameter phi is set to 0, so the maximum fluid load support is 100%. But if you integrated the fluid pressure, you get what we call the plot variable called the fluid force. So if I look at the component along the z direction, and if I actually zoom in on this value, now remember, we happen to pick a contact force which is equal to -1 Newton. So it's easy to see that here we get 1.08 Newton for the force contributed by the fluid pressure. That means we have 108% fluid load support, even though the theoretical maximum is 100% for this particular choice of the parameter phi, the solid to solid contact area fraction. So this is the illustration of the non-physical material model. let's go back to our slides. The way you can deal with this is you can add on the superficial zone a two-dimensional continuous fiber distribution that doesn't have fibers that stick out. If you make it two-dimensional, you can pick the plane of the articular surface or the contact face to be the 2D distribution. So your fibers only lie within this plane. When you do this, you can actually make sure that your fluid load support never exceeds 100%, even the one that is not used in the calculation of the friction coefficient. But if this zone is relatively narrow, as is shown here, actually it's not enough to just pick the planar fiber distribution. You also need to increase the toe region of the continuous fiber distribution, because the high fluid pressure right underneath this two-dimensional fiber distribution will bleed into the two-dimensional fiber distribution. So you can still exceed the 100% theoretical maximum because of the choice of a continuous fiber distribution so close to the contact interface. So you can diminish that by increasing the toe region so that the fibers in the middle and deep zone engage a little bit later than the fibers in the superficial zone. Then the fluid load support will remain below 100%. Okay. Now, what if we want to add friction to our model? So if we want to add friction, we need to set the friction coefficient to a non-zero value. I'm going to illustrate this in a second. And we need to set the solid to solid area fraction to some non-zero value. So let me go and modify not the continuous fiber distribution model. I'm going to go and modify the one with the discrete fibers. So the one with the discrete fibers, we're not going to have any problem with fluid load support exceeding 100% here. Now I want this platen to move back and forth. So that means that among the fixed degrees of freedom, I should now no longer fix the X direction, because I actually want the platen to move in the X direction, which means under the physics menu, I need to add a rigid constraint, which is going to be the prescribed platen motion. That's just the name I'm giving it. And so here for the rigid platen, instead of fixed, I'm going to say prescribed rigid displacement rotation. I'm going to pick the default displacement along X, and I'm going to move by 2 millimeters in the X direction. Then I'm going to move back by 2 millimeters and another 2 millimeters to the left and back to the center. And then I'm going to repeat the cycle. So I'm going to go to the load curve, which is only a scale factor. And under these rigid constraints for the platen motion, I'm going to take the default value, which goes from time 0, it's 0. At time 1, the scale factor is 1, and then it's constant. That means that the platen would move 2 millimeters and then no longer move towards the X direction. So I'm going to change this curve, make it linear, and I'm going to actually add I'm going to add a point at this location, which says at 2 seconds, I want to return back to 0 along the X direction. Then at 3 seconds, I'm going to move at 3 seconds exactly. I'm going to move with a scale factor of -1, which means 2 millimeters to the left instead of to the right. And finally, at time 4 seconds, I'm going to go back to the center. And then I'm going to repeat this cycle. So I can do as many cycles as I want. So if I repeat the cycle, you can see that there will be many more cycles, as many cycles as we. Now, I'm going to run this analysis with uniform time increments, because it doesn't make sense now to use a must point curve here, where the time increments increase by linearly increasing time increments. So instead, what I'm going to do is I'm going to say I want to move. I want for each cycle, for every 2 millimeters, I actually want to decrease the time increments to 0.05. And I'm going to have 200 time increments. So 200 times 0.05 will give me a total of 10 seconds. 10 seconds, which means I'm going to have, remember, for one entire cycle in our case is 4 seconds, right? Going to the right in 1 second, back to the center, second, back to the left in the 3rd second, and back to the center in the 4th second. Okay, so that's 4 seconds per cycle. I'm going to do 2.5 cycles, which means 200 time steps, and I want smaller time increments. This time, I want my time increments to remain uniform, but I want to make sure that the platen reaches the endpoints. So I'm going to keep my must point curve, but this time I'm going to make my must point curve different. I'm going to delete the default must point curve. I'm going to zoom in. And what I'm going to do now is I'm actually going to say I want my time increments to be starting from the very beginning at time 0. I want my time increment to be 0.05. And I want to make sure that I go through time 1. The platen is going to go and I'm going to get a solution at time 1. But I want the time increment to remain at 0.05. And I'm going to do the same with time 2 and time 3 and time 4. So I'm going to put 0.05. And then I'm going to move this like that. I'm going to say at time 3, I also want to have 0.05. And then at time 4, I'm also going to have 0.05. And then I'm going to make this repeat so that if I have multiple cycles, it'll actually repeat itself. I'm going to save this. And in principle, I can run this analysis. Now, this will take longer to run. Oh, wait, I haven't added friction yet. Sorry. Let's go to the contact interface and do the 2 things I said in the slide. Let's change the friction coefficient. So the friction coefficient by default is 0. Let's make it 0.15. This is the equilibrium friction coefficient. And the solid on solid contact area fraction, I'll make it 0.1. And I have the option here to use smooth fluid load support or not. For now, I'm going to use the default of no, but then I'll show you results in a moment on the slide that actually will turn that feature on. So it's going to run this analysis. So it's only 200 time steps, but because it's doing frictional contact, it's not necessarily going to converge as easily. So while it's running, it'll probably take 7 to 8 minutes to run. So we're not going to get to see the final result, but let me just explain to you what we're going to find. So this is what I did. This is how I prescribed the platen motion. And, I should have added more plot variables. I forgot to do that. But contact stick, if you have slip stick, which will not occur significantly for the first 2.5 cycles, but as time progresses and the fluid pressure drops, we will have that. So anyway, and let's look at the results. So for the solution of the problem that I just showed you, we're going to find that the friction force increases from time 0 to time 1 because why? Remember, we're increasing the contact force from 0 to 1 Newton in compression from time 0 to time 1. So the friction force will increase in proportion. You can tell that the friction coefficient is on the order of 0.03. It's very low because we're dividing 0.03 by the 1 Newton contact force. But then we have a reversal of direction. So the blue curve reverses direction. The friction force is in the negative direction because the platen is moving now to the left. And then it reverses again. But over time, you see that there's a slight increase in the friction force. That's because the fluid pressure is slowly dropping. So if we were able to run this for longer, and it would take hours to run, thousands of cycles, we would get a more realistic dependence, more similar to the experimental results that I showed. In fact, I'll show you those results in a slide in a moment. If you decide to use the smooth fluid load support, that means that instead of using the nodal value of the fluid pressure at the contact interface, this nodal value is subject to noise during the contact analysis. So instead, you can take the fluid pressure at the center of the element that's right underneath the contact face. And then that fluid pressure will be smoother than the nodal value. Then it turns out that you actually have a slightly less friction force. Which one is more accurate? Honestly, my instinct would say that the smoothing the fluid load support is fine, as long as you have a boundary layer near the articular surface, the contact interface, so you have a very thin element. So the fluid pressure in the element is much closer to the fluid pressure at the contact interface. If you have a coarse mesh, then you should not really use smooth fluid load support. Anyway, this is the result for smoothing the fluid load support, in which case you would just pick this option. And this would be the friction coefficient, which is the absolute value of the friction force divided by 1 Newton. And we take the absolute value. So what you see is the friction is a little noisy, but increases over time when you don't turn on the smooth fluid load support. If you do smooth fluid load support, you get a smoother response. It's not perfect, but it's smoother. So I just want you to know, biphasic friction analyses will take much longer to converge than just the creep analysis that you saw earlier, because it struggles to, not distort the elements too much. So we're not going to get to the final solution here, but I can plot the intermediate results. And before I do anything, I'm going to just show you the platen moving, right? You can see the platen. Let me turn on the mesh. And if we actually look at, this view, you can actually see the mesh distorting as you move to the right and you move to the left, you can see a little bit of the mesh distortion. If you want to exaggerate the mesh distortion, you actually have the option to scale the displacement of the mesh, which is the displacement map here. I can scale it up by a factor of 10 along X, Y, and Z. If I do this, you can see much more deformation. This is because I scaled up the motion. You can see the platen motion is also increased. So you can see how the frictional contact will cause the sample to sway back and forth like that. So that's with the exaggerated displacement map. I'll go back to the default map. And if I were to select the face here and I can say post, new graph, I can request to look at the contact force along the X direction. So you can see the contact force increases at first and then, reverses direction. So you can see we haven't finished one complete cycle yet because we're less than 4 seconds, but it's not too bad. And the contact force in the Z direction is the force that we prescribed. We made it ramp up from 0 to 1 Newton in compression for over 1 second, then it stays constant. So it's nice to confirm this. And if you're interested in, let's say, the fluid load support, this is the average of the local fluid load support. You can see this is a little bit of noise during the reversal that occurred. So this is why the friction coefficient will sometimes be a little bit noisy, because the code will struggle a little bit, especially if there's a little bit of stick slip with the narrow elements that we have on the edge. So you should be aware that the contact algorithm will struggle a lot more when you add friction than when you don't have friction. Okay. And the local fluid load support for the element that I happen to pick doesn't have noise. So that means that there are some elements at the edges where the local fluid load support is actually going very negative. And I can play this slowly. You can see right now, these values are well behaved. They're between 0 and 1. But once we get close to the reversal of the load, you're going to see at some point, it could shoot down to a negative value. I don't know if we're going to see it here, but we'll see it at the end of the reversal. I think right here, you see? So here, you're getting hugely negative values. That's because of, stick slip occurring at these elements. Again, I can hide the rigid platen. So if this bothers you, of course, you can just, decide that, well, it gets averaged out anyway when you calculate the friction force and the friction coefficient, but that's just the fluid load support, because really it's dividing by contact traction, which is approaching 0. That's why you get a very long drive. But then it goes pretty much back to the range 0 to 1 as the sliding continues in the reverse direction. Very good. So that's bringing us to the end of this presentation. So I want to remind you, this is the experimental data for the fluid load support and the friction coefficient. And I told you it takes a long time to run these analyses, for the number of cycles that take us to 5,000 seconds of loading. But we did that for the paper that we published this year. So if we actually run this analysis, I'm going to show you that actually we did the analysis for up to 5,000 seconds of loading on FEBio, and these are the parameters that we use for this particular FEBio analysis. They mimic the experimental study, and these are the FEBio results. This is the friction coefficient normalized by its equilibrium value, and this is the fluid load support, and they're very similar to the experimental value. So we were able to run the analysis up to 5,000 seconds, but like I said, it took a long time on a high-performance computing cluster. We also used this, FEBio Studio to explore another experiment that was done by the same authors, the same student, a year later, where the load on the platen was not static, but it was dynamic. So the compressive load is varying up and down between a low value and a high value, and we're sliding at the same time. So the creep displacement for this platen is, kind of similar to the average of the creep displacement under a static load, but the friction coefficient oscillates a lot. And we discovered, thanks to, the FEBio Studio analysis, that that's because we actually have suction negative fluid load support, which is not just noise in this particular case, it's legit during part of the cycle. And this is the FEBio solution. This is the experimental data. Once again, you see very good agreement in the creep displacement and in the frictional response between FEBio and the experimental data. And as I said, you really are not limited to doing biphasic frictional contact between a rigid platen and a biphasic material. You can also do biphasic on biphasic. So this particular model, you can find it in the repository. I'm not going to show you how it was created and all, but you can find it in the repository. It was created entirely in FEBio Studio with no external meshing software or CAD software. And if you actually recognize that you have two biphasic surfaces on either side, that means that when you actually plot the fluid load support, you actually have a fluid support on, let's say, the bottom strip, that's the blue curve, and the top component, which we call the plug. And they're not going to be exactly identical because of the mesh. It's a discretization of the real geometry. And so when you average the fluid load support on this mesh for the strip and then the yellow mesh for the plug, you get tiny, tiny differences. Thankfully, they're not big enough. And when you look at the friction coefficient here, in this case, you can see a little bit of noise, but again, remember, this is the friction coefficient compared to the value of 0.15, which is the equilibrium friction coefficient. So it turns out that the fluid load support is even higher when you have biphasic on biphasic contact, and the solid to solid contact area fraction is lower. So your friction coefficient is even lower. And this also agrees well with experiments. Okay. So let me thank you for watching this webinar, and I'll remind you the FEBio team consists of Professor Jeff Weiss at the University of Utah, Dr. Steve Moss, who's the main code developer, Dr. Ben Ellis and Michael Herron, and myself, who gave the presentation. We're supported by the NIH for the FEBio software. And I'll remind you that you can find all of the resources that you need on the FEBio.org website. You can have, for example, you can ask questions on the forum. And if you have plugins, if you create new features that you want to share with the general user community, then you can also post your plugins at this particular location. Thank you once again for watching this webinar, and I hope to see you at the next one.